Hello, my name is Renfred Sulit, and I'm going to present to you my presentation, Newton's Law of Motion. What is that? Newton's laws of motion are three physical laws that describe the relationship between the motion of an object and the forces acting on it. These laws, which provide the basis for Newtonian mechanics, can be paraphrased as follows. Number 1. A body remains at rest or in motion at a constant speed in a straight line, unless it is acted upon by a force. Number 2. At any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalently, the rate at which the body's momentum is changing with time. Then last, if two bodies exert forces on each other, these forces have the same magnitude but opposite directions. The three laws of motion were first stated by Isaac Newton in his Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy, originally published in 1687. Newton used them to investigate and explain the motion of many physical objects and systems. In the time since Newton, new insights, especially around the concept of energy, built the field of classical mechanics on its foundations. Limitations to Newton's laws have also been discovered. New theories are necessary when objects move at very high speeds, or special relativity, are very massive or generally relativity, or very small quantum mechanics. The prerequisites. I think it's prerequisites. Correct me if I'm wrong. Newton's laws are often stated in terms of point or particle masses, that is, bodies whose volume is negligible. This is a reasonable approximation for real bodies when the motion of internal parts can be neglected, and when the separation between bodies is much larger than the size of each. For instance, the Earth and the Sun can be both approximated as point-like when considering the orbit of the former around the latter, but the Earth is not point-like when considering activities on its surface. The mathematical description of motion, or kinematics, is based on the idea of specifying positions using numerical coordinates. Movement is represented by these numbers changing over time. A body's trajectory is represented by a function that assigns to each value of a time variable the values of all the position coordinates. The simplest case is one-dimensional, that is, when a body is constrained to move only along a straight line. Its position can then be given by a single number, indicating where it is relative to some chosen reference point. For example, a body might be free to slide along a track that runs left to right, so its location can be specified by its distance from a convenient 0 point or origin, with negative numbers indicating positions to the left and positive numbers indicating positions to the right. Newton's first law. Newton's first law expresses the principle of inertia. The natural behavior of a body is to move in a straight line at constant speed. A body's motion preserves the status quo, but external forces can perturb this. The modern understanding of Newton's first law is that no inertial observer is privileged over any other. The concept of an inertial observer makes quantitative every idea of feeling no effects of motion. For example, a person standing on the ground watching a train go past is an inertial observer. If the observer on the ground sees the train moving smoothly in a straight line at a constant speed, then a passenger sitting on the train will also be an inertial observer or inertial observer. The train passenger feels no motion. The principle expressed by Newton's first law is that there is no way to say which inertial observer is really moving and which is really standing still. One observer state of rest is another observer state of uniform motion in a straight line, and no experiment can deem either point of view to be correct or incorrect. There is no absolute standard of rest. Newton himself believed that absolute space and time existed, but that the only measures of space or time accessible to experiment are relative. Newton's second law. By motion, Newton meant the quantity now called momentum, which depends upon the amount of matter contained in a body, the speed at which that body is moving, and the direction in which it is moving. So this is the presentation, looks like this. So A means acceleration, F is mass, and F is force, and mass, M is mass. So there's kind of like Newton's second law, which is moving in a straight line and direction too. In modern notation, the momentum of a body is the product of its mass, and its velocity p equals mv, where all three quantities can change over time. Newton's second law, in modern form, states that the time derivative of the momentum is the force F equals dp over dt. If the mass does not change with time, then the derivative acts only upon the velocity. So the force equals the product of the mass and the time derivative of the velocity, which is the acceleration, F equals m, dv over dt equals ma. As the acceleration is the second derivative of position with respect to time, this can also be written F equals m d squared s over d t squared. So see you for part 2.